Hi everyone, this is Dr. Swaminathan SM, Associate Professor, ECE Department, SNS College of Technology. Now I am going to discuss about the topic called steady state error in linear control system. So first, a review about the previous class we will discuss. Next, a steady state error that defines if the output of a control system at a steady state does not exactly match with the input. The system is set to steady state error, that is called the steady state error. Next, classification of control systems. Next, the steady state error of unity feedback systems. Steady state error constant in the position level, velocity level, and acceleration level. So Kp, Kv, Ka. P stands for position, V stands for velocity, and A stands for acceleration. Following with the example, we close. So the steady state error already we discussed. Any physical control system suffers a steady state error in response to the certain types of inputs. That is called the steady state error. A system may have no steady state error in the step input. The same system may exist non-zero steady state error to a ramp input. That is called the steady state error. So next, the classification of control system. We discuss about the classifications, that is three things. One is called step inputs, another one is ramp, and another one is parabolic. So the magnitudes of the steady state error due to these individuals may inputs are indicative the goodness of the system. So the classification of the control system for unity feedback with the open loop transfer function following G of S. And next, it involves the S power n is the denominator, and it represents the n poles at the origin. So a system is called 0, type 1, type 2 based on the n, capital N, that is poles of the origin. As the number is increased, the accuracy is also improved. And next, increasing the type that aggravates the stability problem. So a compromise between the steady state accuracy is relatively important. So the steady state error of unity feedback system is called the given system, that is R of S is the input, E of S is the error system, G of S is the gain of the system, and C of S is the output. So C of S, output divided by input, called the transfer function. G of S divided by 1 plus G of S. So we have given the G of S and 1 plus G of S we have find. So the transfer function between the error signal and the output signal, that is input signal, is called E of S divided by R of S. And the final value theorem, it provides a convenient way to find the steady state performance of the stable system. So E of S is equal to, you can find E of S. So R of S goes right hand side. And next, the steady state error, that is ESS, that is SS means steady state, E means error. So limit t tends to infinity, E of t. And next, limit S tends to infinity, S into E of S. So you just substitute the E of S value here. The steady state error constant that fights between the merit of control system. The higher of the constants, the smaller steady state error. So in a given system, the output may be the position, velocity, pressure, temperature, or any other, and therefore it can call the position of the rate of change of the output velocity. So it means the temperature control system, position represents the output temperature, velocity represents the rate of the change of the output of the temperature, and so on. The steady state error for the unit step input is called limit S tends to 0, S divided by 1 plus G of S into 1 by S. So you can get the 1 divided by 1 plus G of 0, because S tends to infinity. S is cancel. S tends to 0 means, so just to substitute the value, S is equal to 0. So G of 0. And the static position error constant Kp, that is limit G of S, C of S equal to 0. So position constant 1 divided by 1 plus Kp. So the Kp that defines the value, you can get the K value, the type of one order systems, and Kp value for steady state error ESS, and ESS equal to 1 by 1 plus K for type 0 system. 0 means type one system. So following the activity, we will go for the static velocity error constant kV. So ESS equal to limit s tends to 0, s divided by 1 plus g of s into 1 by s square. So s into g of s, kV is defined by kV is equal to s into g of s, that is s tends to 0. So steady state error in terms of the static velocity constant is given by kV. So kV, that is limit s tends to 0, s into k, tksa, that is tas plus same like for tb, and denominator term t1 and t2. And next the types 1 system, just a value, that is ts plus 1 and t1s plus 1 plus t2s plus 1. For type 2, it can make the infinite. So the ramp input of the steady state error ESS, ESS equal to 1 by kV, that is infinite for type 0 system. For type 1 system, 1 by kV velocity error, velocity constant, that is error constant, type 1 system equal to 1 by k. And type 2 system, that is 1 by kV, that is equal to 0. So the steady state error of the system for parabolic input, that is s divided by 1 plus g of s into s 1 by s cube. So first we will see 1 by s, and next 1 by s square, and next 1 by s cube. This is for the acceleration ka is defined s squared into g of s. And before velocity we will discuss s into g of s, and next g of s, same thing. Okay. So first 1 by s and next 1 by s square, next acceleration means 1 by s cube. So ESS equal to 1 by k for type 0 system, for type 1 system, for type 2 system. So based on this you can make the 0 and again the 0, and type 2 system it is k, and type 3 system it is infinite. So the static error constant we will discuss about the static error. Infinite means type 0 1, and 1 by k means type 2, and 0 means type 3. For steady state error we can discuss. So in the steady state error constant, R of s is the input, E of s is the error, G of s is the transfer function, that is gain of the system, C of s is the output. So the steady state error G of s divided by 1 plus G of s, just to substitute the value, and E of s equal to R input minus output. So E of s you can find R of s into divided by 1 by G of s. So just to substitute the value here, and you can find the different signal. So unit step signal for steady state error constant 1 by 1 plus Kp. For Kp, that is error constant limit s tends to 0, G of s, and 1 by Ka, that is Kv for unit ramp signal, that is Kv is equal to limit s tends to 0, G, s into G of s. Again parabolic means s squared into G of s. So Kp, Kv, Ka, that is called position, velocity, and acceleration error constant. So you can make the example for given system. R of s is the input, and G of s we can have the system G of s, and C of s is the output. So these are all the system having Kp, Kv, and Ka. So these are all the Kp, Kv, Ka limit based on the given formula. G of s means Kp position, Kv means s into G of s, Ka means s squared into G of s. So you can get the different values for the Kp, Kv, and Ka. So ESS error constant you need to find 1 by 1 plus Kp. So 1 by 1 plus infinite, that is equal to 0. ESS equal to 1 by kV, that is 1 by infinity also 0. ESS equal to 1 by Ka, that is 1 divided by 10.4, that is called 0.09. So this is called the 0.09. And again summary, you can make the type 0 system, type 1 system, and ramp input, you can make the ramp input, and for the parabolic signal we can make the ramp signal. So these are all the important concept for error constant. Thank you.